I hope by now that you have downloaded our free simulator program from this website. It will make it much easier to follow the tutorials as we continue. To gain the full benefit of the tutorial, you should use the simulator to experiment with circuits of your own. We continue to look at transistors, and this example uses both an NPN and a PNP transistor to create a flashing LED. Initially, both transistors are off. When we switch on, the key player is the capacitor, which charges slowly through the 13K ohm resistor. Once the voltage at the base of the NPN transistor exceeds 0.7 volts, it turns on. This turns on the PNP transistor, causing current to flow through the LED. Almost immediately this drains the capacitor, switching the NPN transistor off again, which in turn switches off the PNP transistor. The capacitor begins charging again, repeating the process. This type of circuit is known as a multivibrator. This multivibrator has two capacitors, two NPN transistors and two flashing LEDs. At the start, both transistors are inclined to turn on, but one will be instantaneously faster than the other. Suppose TR1 turns on first. The base of TR2 is then immediately connected to the negative end of the battery, which we call ground, through capacitor C1 and the collector emitter of TR1. So TR2 turns off. C2 will begin charging until it opposes the battery sufficiently to lower the voltage at the base of TR1 to below 0.7 volts. Now TR1 turns off. TR2 is no longer connected to ground, so can turn on. It begins charging C1 while C2 discharges through the 3K resistor and a collector emitter of TR2. When C2 has discharged sufficiently, it allows TR1 to turn on again, turning off TR2. The process repeats. We switch on and see the effect. Whenever a transistor turns off, the LED above it dims. This example includes two polarized capacitors. This means that it's important to connect them the right way around. Generally, the negative end is marked with a 0. We have placed two oscilloscopes to monitor key voltages. When we switch on, we see these distinctive curves. The first oscilloscope monitors capacitor C1. We see it charge to near full capacitance before TR2 turns off. Then it discharges before repeating the process when TR2 turns on again. The second oscilloscope shows the voltage at the base of TR2. While TR2 is off, this shows the voltage of C1, which is now like a small battery. However, it is inverted because its positive end is attached to the TR2 emitter, and the negative end is attached to the TR2 base. As C1 discharges, the voltage at the TR2 base increases until it reaches plus 0.7 volts, and TR2 turns on again, thereby turning off TR1. To understand the process fully, test the voltage and current at key points. The curious thing about the unijunction transistor, or UJT, is that the emitter is located where you would expect the base. The other two leads are marked base 1 and base 2. The original name for this device was double base diode, which is more descriptive. Figure 2 shows a representation of the UJT consisting of a diode and two resistors. Initially the diode is off, so no current flows at the emitter. When the voltage difference between E and B1 exceeds a percentage, in this case 77%, of the voltage difference between B2 and B1, the UJT turns on. At this point the emitter conducts current, and simultaneously the resistance between E and B1 drops to a low level. The ratio at which the UJT turns on is called the intrinsic standoff ratio, and is designated by the Greek letter eta. This UJT turns off when the voltage difference between E and B1 drops below 2 volts. Once the capacitor has charged sufficiently through R1, the UJT turns on, allowing the capacitor to discharge through R2. When the voltage difference between E and B1 drops below 2 volts, the UJT turns off, allowing the process to repeat. Remember, the time taken to charge the capacitor to 63% of capacitance is resistance times capacitance, or 13,000 times 1 millionth equals 1/77th of a second. Because R2 is small, the capacitor will discharge quickly, so we expect around 70 oscillations per second. Because this would be too quick to see on the oscilloscope, we have slowed down the simulator to 1/10 speed to show the waveform. This device is useful because it requires only one transistor to create the oscillation and because it can oscillate at high speeds. We turn our attention to integrated circuits, or ICs. There are 3 shown here. Each can have internally many of the devices we have seen, but miniaturized so that large and complex circuits can be accommodated. ICs are designed to perform specific tasks as described by their manufacturers. Because of their speed and reliability, they simplify the design and building of larger circuits. We are going to examine the use of one of these ICs, the small one on the left. This is the well-known 555 integrated circuit. By combining the 555 timer integrated circuit with a capacitor and selected resistors, it can be used for a variety of timing purposes. By convention, one end of an IC has a notch, and pins are numbered anti-clockwise from there. In this device, pin 1 is connected to ground, the negative end of the battery, and pin 8 is connected to the positive supply. Pin 3 is the output pin. Initially it is connected internally to ground, so its voltage is 0. When the IC is triggered electronically, it is connected internally to the positive supply, so its voltage equals the voltage of the battery. Pin 2 is the trigger. When the voltage at pin 2 drops below 1/3 of the supply voltage, the timer turns on. To switch the 555 IC off requires the voltage at pin 6 to rise above 2/3 of the supply voltage. Pin 4 should be connected to the positive source. Pin 7 is the discharge. Pin 5 is really used. We show the 555 being used as a timer. Pin 4 should be connected to the positive source. Pin 2 is the trigger and is connected to the join between the capacitor and the resistor. Initially the voltage at pin 2 is 9 volts, but as the capacitor charges, the voltage at this pin drops. When it drops below 1/3 of the supply voltage, the 555 IC will turn on. Start the process to watch this occur. It takes R times F, which is 10K divided by 1000, equals 10 seconds for the capacitor to reach 63% of capacitance, so it takes a little more than this for the timer to turn on. The 555 will remain on even if the voltage at pin 2 rises above the 1/3 level again. To switch the 555 off requires the voltage at pin 6 to rise above 2/3 of the supply voltage. In this example it is tied to ground, so the 555 cannot turn off. So the timer can be made to delay for a desired length of time before switching on. Here we show the 555 as an oscillator. Initially the 555 turns on because the voltage at pin 2 is low. The capacitor begins to charge. Pin 6 is connected to the top of the capacitor, and when its voltage rises above 2/3 of the supply voltage, it causes the 555 to turn off. While the timer is off, pin 7 is connected internally to ground, which allows the capacitor to discharge. When the voltage drops below 1/3 of supply voltage, the timer turns on again. The process repeats. Pins 2 and 6 carry no current. Pin 3 connects alternately to ground and the supply voltage, causing the 2 LEDs to flash. When pin 3 is connected to ground, the upper LED turns on, but the lower LED turns off. when pin 3 is connected to supplied voltage, the upper LED turns off and the lower LED turns on. The current flowing from the output pin 3 shows a distinctive square wave. Current is either flowing at a constant rate or no current is flowing at all. Because the capacitor charges through R1 and R2 and discharges through R2, a formula for the frequency in hertz or cycles per second is given by this equation. Using this formula, you can verify that the frequency of the previous example is little over 3 cycles per second. The full cycle is measured from when pin 3 turns on until the next time it turns on. To recap, when the timer is on, pin 3 is connected internally to the power supply. When the timer is off, pin 3 is connected internally to ground. By varying the resistors R1 and R2, one can alter the duty cycle, or the proportion of time that the timer is on. In this example, R1 equals 20k and R2 equals 10k. This gives a duty cycle of 75%. The formula for calculating the duty cycle is given by this equation. That concludes part 5 of the tutorial. In part 6 we will be looking at waveforms including sound waves.